Hello, everyone. I'm Andrea Ray, and I'm giving the talk on transition or research to a range of applications, R2X, X where that means operations, applications, and various kinds of use. I have several subject matter experts that will be joining us in the panel discussion during the actual review. Their names are there, and I'll introduce them as I go through. What is R2X at PSL? It's really rooted in foundational and use-inspired innovation research and across all the three themes: extremes, water, and marine resources. PSL science planning looks towards the NOAA mission and to use by either other researchers or in operations, or knowledge use by NOAA or other agencies and groups like the National Climate Assessment. We track categories of transition outputs. I'm not going to be labeling these to the most part, but I just want to make you aware of some of the NOAA tracking. And we also track several stages in transition, not just the final handoff. So that's things like a proof of concept, testing as a demonstration or as a pilot, tested in an operational setting, or a documented uptake of a knowledge transfer, like a paper or a report might be the documentation, but how is it actually used by somebody? We do a lot of iteration with core users and operational partners. By core users, this is a term that the Weather Service uses as well. I mean, some of these core partners who we're actually working to transition with. There's a lot of other partners for a lot of other regions. So that includes things like the Weather Service, National Centers for Environmental Prediction, NOAA test beds, which are an actual an activity between researchers and forecasters, weather forecasters, and some other groups that I'll be talking about. We also work with the Fisheries Science Centers and their regional offices, with the NOAA Regional Integrated Science and Assessments, and the Department of Interior Climate Science Centers. One of the other things we do is we actually reflect back. We get information. O to R is operations to research, or M to R, management needs to research. So those are other things that we do. And we think of this as being beyond a consultancy role, like beyond being told this is exactly what we need, go do it, as for example, a contract. These relationships actually spur use-inspired R&D aimed at NOAA operations overall. So PSL contributions are often an early link in a chain of transition to operations, service intermediaries, and end users. So a few examples: model improvements at PSL go to NCEP and to, for example, the National Water Model forecast some products. Those improve forecasts by NCEP, the Weather Forecast Centers, or River Forecast Center, then might get fed out to water management or emergency manager users or recreation to the ultimate use. Weather Forecast Office flood statements, for example, may then go out to the public and the media and emergency managers for the safety of lives and property. Our work on experimental predictions and guidance, for example, drought research and product development, might go out via NIDIS, the National Integrated Drought Information System, or the Drought Monitor, or NOAA's Drought Outlook, and that then might get used by state drought agencies or for drought preparedness and mitigation efforts. Another example might be that drought information goes out to FuseNet, that's the USAID Famine Early Warning System network, and that goes out to uses in food security abroad and national, and ultimately national security as that relates to international relationship. Another way that those drought information might get used is situational awareness for extremes for emergency managers. A third example is forecasts and projections of ocean conditions. This is our work with NOAA Fisheries. These can be integrated into fisheries policy decisions and fisheries management, and that might then affect commercial fisheries economic decisions, and in turn benefits coastal economies and food security. Types of transitions at PSL, and this will be the organization of the rest of the talk. We improve NOAA operational experimental models. We do things like model diagnostics and evaluation. We develop the tools to do this, or we use them. We develop things like new parameterizations for models. Specific improvements have been transitioned into operational models, including the UFS, the HER, the GFS, and the National Water Model. And I should just note right now that I'm not spelling out all the acronyms, but you'll find them in the notes below. We also do experimental predictions and guidance, and these may be provided directly to certain sets of users as from the PSL web pages, as well as being provided, for example, as guidance to the Weather Service or eventually transferred to the Weather Service. We do a lot of what we call knowledge transfer, things like synthesis and assessments, and it's really a big activity at PSL. Much of it is co-production with internal and external users. Co-production is a word that's used a lot by social scientists to mean that you're really working together to create the knowledge. And we provide support for the NOAA Fisheries and Ocean Services, other federal and state agencies, and a number of other places like the state of Colorado. We also do things like analysis tools, which are used to diagnose and analyze and visualize the data sets. And these are often supported for ongoing use at PSL. And while they're involved in things that become transitions, they're usually not transitions themselves, although their use may be transition. So as I said, this is forming the organization of the rest of the talk. Starting now with improvements to Weather Service operations, we think of ourselves, if you remember that old ad slogan from BASF, well, we don't make the models usually, but we make them better. And I'm going to talk about three. Starting with the Wind Forecast Improvement Project, it was a field program, you've heard about it a few times in other talks, to improve short-term weather and wind forecasts for renewable energy. It's resulted in a number of transitions, including parameterizations that are operationalized in the HER. It's a long partnership going back to WFIP-1 with the Department of Energy and other OA labs, and in particular, the private sector has partnered on this. One of the indicators of satisfaction is that DOE has returned to support and work with us on WFIP-3, which will be offshore wind, coastal and offshore wind. And then it's also received a NOAA Technology Transfer Award for improving forecasts of turbine height winds and solar irradiance in HER. This project has resulted in multiple kinds of transitions. This slide, we'll see a couple more like this for different projects, is a kind of logic model for organizing the inputs, the actual activity, and the outcomes and outputs of a project. On the left is research partnerships, capabilities in model diagnostics and evaluation, observing systems and designing field campaigns. WFIP is the activity. And over on the right, transitions and other benefits. Some of the things that have occurred have been actual transitions to the Weather Service, like physical parameterizations of the HER and the RAP models. Another one is we originally diagnosed the biases in those and worked with the global systems labs to correct and develop those parameterizations, and then to make sure that they didn't make anything work when you used them nationally. The real-time observation-based model evaluation tool is used to do all of this and is available for use by anyone. There's a gap flow tool used by the Weather Service in Portland to forecast when there are going to be strong winds coming through the Columbia River Gap. And there's a ramp tool for wind companies to better understand when and forecast when there might be increases or decreases in wind. We acquired radars that were bought by the Department of Energy, but then they were transferred to NOAA. HER microphysics I've mentioned. And then the results and experience in this whole field experiment are now informing the development of WFIP-3, which will be coastal and ocean wind forecasting. A second example is the 20th Century Reanalysis, the version 3. Down at the bottom, you can see it was released in 2019. There have been several versions. The challenge in this case was that there was a need for a long time series of weather for scientific studies of weather and climate, going back before the traditional instrumental record and in places where there's been very little instrumental record. So this project, going on since the mid-2000s, has reconstructed over 200 years of weather. The research data set and data assimilation methodologies are maintained at PSL, but used by many other people. there's been a lot of creativity going in this to find and incorporate old sources of observations. For example, a citizen science effort to scan old ship logbooks. One of the indicators of success for this project has been, just since 2015, around 1,500 peer-reviewed articles cite the use of the data set or its methodologies. One of the top papers is the release of the version 3, and the full citation is in the notes. On the left is an example of a reconstruction from February 1936, which is one of the coldest Februaries on record, and it shows you how what the weather map, a reconstructed weather map, would look like, and the colors indicate the confidence in all of the reconstructed observations there. So there are multiple kinds of transitions of this project too. A really important one is a long research partnership with EMC, so that we could talk to them about how they might use this, and over time how they have used it. Data assimilation capabilities, both of those are two-way arrows because those have continued. Both we've improved data assimilation capabilities as well as having experience in those to begin with. And of course, this need for a long surface-only climatology. There's actually been 3 versions of this. The early one came, and so with each version, there have been updates and upgrades that are based on the interactions with EMC, but with a lot of other users as well. Some of the transitions and other benefits are a proof of concept of the Ensemble-Kalman filter data assimilation for EMC. In the mid-2000s, they hadn't been using this. It was a fairly new kind of technique. And so using that filter as testing it as a data assimilation method for the 20th century reanalysis gave EMC, Environmental Modeling Center, confidence that it was something that they might want to use, and then they tested it themselves and decided to use it operationally. So our PSL's originally 20th century reanalysis Ensemble-Kalman filter code was the basis for the operational code that's later been implemented at EMC. There have been a number of improvements to the operational GFS by being able to use this as a verification data set. It provides an instrument-based link between paleo reconstructions and climate data, because we've got data, reconstructed data that go back that you can compare things like tree ring reconstructions to. One of the things that's been an unexpected spinoff, looking at the reanalysis, they discovered that there was a problem with the stratospheric ozone parameterization, and actually by using this, developed a new parameterization that's being run at INSEP. We also know it's got a number of private sector uses, and it's being used as a wind climatology for renewable energy to know when to know what kinds of periods in the past there have been either low or high winds, and to be able to adapt the wind development for that. It's also been used to constrain heat flux over the oceans, which is a goal of the Precipitation Grand Challenge. And the hurricane reanalysis, being able to look at the weather maps and find hurricanes before the main record, and in places where there was perhaps nobody there to observe it. The third example is the Advanced Quantitative Precipitation Information System, AQPI. This comes out of a long history of collaboration with water managers and weather service people in California and on the West Coast. And the challenge has been forecasting extreme precipitation, in particular atmospheric rivers, or ARs, that provide water supply but also cause flooding. Orographic rainfall, or rainfall affected by mountain terrain, is not detected by radars and not well forecasted in the multi-radar, multi-sensor system used by the Weather Service, or Mountain Mapper, also used by the Weather Service. AR impacts include that just a few events in the winter season can provide 30 to 50% of California's annual precipitation. The annual average of damages is over $1 billion, and that accounts for over 80% of flood damages across the western US in an average year. Sea level rise and urbanization, especially in the San Francisco Bay Area, may exacerbate the problem. It's a regional effort, but it has national benefits for improving extreme precipitation forecasting and decision support in the 1 to 12 hour time frame. It addresses the NOAA Grand Precipitation Challenge goal weather-ready nation and supports Weather Service integrated decision support and coastal preparedness. The slides over here are a satellite remote sensing generated graphic of an atmospheric river with, of course, the California coast being on the bullseye there. And then this is a map of the San Francisco Bay Area, which is vulnerable because it has over 7 million people and over 350,000 people in the 100-year floodplain, and $46 billion in exposed structures in that area. So this is another of those logic models, and some of the things that went into this are really the trust developed with state and regional and local water and flood control agencies from earlier projects that PSL has been involved with. The state of California provided the bulk of the funding for the targeted observations and research being done here. There's also our experience with doing process studies and designing observing systems and capabilities with model diagnostics and evaluation. AQPI itself is a suite of observations, modeling, decision support services integrated together, and innovation in research for forecasting extreme precipitation and flooding. Some of the transitions and other expected benefits are just being able to just starting because we're 3 years into a 4-year project. A big one is the science, the advanced process understanding of ARs and other coastal and orographic processes. The targeted observations are being used in research right now in evaluations to assess model issues for precipitation. However, we're expecting them to improve the HER model for 1 to 12 hours, and in particular for just the first several hours when it's really important to have a heads up of flooding. All the data is being made available through the Atmospheric River Portal and through other Weather Service operations via MADIS, the Weather Services system. And a real advance is that the partners, the various water districts around San Francisco Bay, are providing their data into the system, and they're able to get the data from each other as well as provide it to the Weather Service. There's a precipitation analysis tool that's been developed and being used to improve on those Weather Service gauge radar products that I mentioned, the MRMS and Mountain Mapper. It's being used already by the state of California for early warning, decision support, and preparedness. There are other regional benefits for flood mitigation due to these early warning and decision support service. An unexpected user was the wastewater managers who said, wow, if you knew that there was going to be a lot of water, we were going to have a heavy rainstorm, we'd adjust how we were running our sewage systems so that we wouldn't be adding that water on top. It's been a proof of concept for gap filling radars. Gap filling radars are those that come in and are positioned so that they see places where the main Weather Service radars can't see. It's being used for evaluation of national water model forcing. And as I mentioned before, it has national benefits in extreme precipitation and hydrologic forecasting, even though it itself is a regional project. So next, experimental products and services, and these we think of as really pushing the envelope on NOAA's forecast capabilities, and I'll be talking about 3. First is the subseasonal to seasonal forecasting, or S2S, 2 transitions that we're working on with the Climate Prediction Center. S2S forecast skill is really low in a lot of places, but especially in the Western US. And it's highly relevant for natural resource management, the energy sector, and other uses. And it's in particular important for longer range situational awareness for many sectors. 2 of the examples that have been covered somewhat in other talks is the winter season precipitation forecast. There's an example of that on the left, and focus on the cold season because of the importance to Western water management, and a suite of linear inverse modeling forecast tools for week 3 and 4 CONUS surface temperature forecasts. Part of the reason for highlighting the S2S forecast is to talk about the collaboration with the Climate Prediction Center and why that's been integral to improving the S2S forecast and other research. We've been collaborating with them for many, many years. One of the things has been participating and in 2015 hosting the annual Climate Diagnostics and Prediction Workshop. CPC Director Dave DeWitt has been visiting PSL for about a week every year and having conversations with many people, giving talks. He gives a talk. Matt Newman and Tom Hamill have made a number of visits to CPC in the last several years, and we've had a person detailed to CPC. David DeWitt also assigned a staff person to work in particular with Matt Newman. Service activities benefit PSL's understanding of needs. So, for example, PSL have served on the U.S. CLIVAR panels with CPC personnel, and that's increased or enhanced the collaboration. The winter season guidance that I mentioned before has been regional funding, but it's been leveraged to develop a CONUS-wide product and improvement in skill. And both of these projects also build on PSL's longstanding collaborations with water resources managers. For example, that winter season guidance is issued in hydrologic units, which are the units preferred by RFCs and water managers rather than the climate divisions that we use or point forecasts that we use for some other kinds of things. I want to talk a little bit more about the LIM, the linear inverse modeling. One of the things that's happened is they have regularly participated in the weekly CPC week 3 and 4 outlook discussion. PSL staff have also long participated in the drought and seasonal forecast calls. We've been virtual before virtual was cool, and this has resulted in research to understand processes, predictability, and skill. I want to show these figures because I want to make the point that what we originally had discussed providing to CPC is this 2-meter temperature anomaly and probabilistic forecasts. But as we were on those week 3 and 4 calls, it became obvious that what was really useful to CPC and their forecasters was not just that final output, but a suite of things that go into producing that and to assessing where the skill is and other aspects. So as a result, we now produce a suite of ancillary, well, we were producing them before, but we provide a suite of ancillary information that allows CPC to have more confidence in these forecasts as part of their larger forecast process. The second example is the evaporative demand drought index. The challenge here has been operational monitoring of the demand side of drought at user relevant time and space scales. The benefits are improved drought, early warning, and ongoing monitoring of things like flash drought and fire weather prediction. The funding has come from NIDIS, the National Integrated Drought Information System, the NOAA Weather Program Office, and the NOAA Climate Program Office, and it's been transitioned to the National Water Center just last year. It's produced daily at NOAA, and we generate a number of value-added products. There's a screenshot of the product. It's the evaporative demand at a specified time scale for a location. So this slide illustrates the timeline from the idea to product for the EDDI. And in about 2009, Mike Hobbins, who's one of our panelists, so we can talk more about that with him, was working at the Colorado Basin River Forecast Center and working on dynamic ET estimates for stream flow. And he noticed something interesting about the Texas 2011 drought and regional high evaporative demand. So he started working on that. And he got funding from NIDIS, and among other things, provided an early version of EDDI weekly to the Colorado Climate Center. And then they, in turn, provided it to a number of their stakeholders, including the State Drought Task Force. So the product was enhanced and retooled based on that feedback. And also, Mike came to join us at the Physical Sciences Laboratory as part of that funding. And then a couple of years later, we got funding from the Weather Program Office from the Joint Technology Transfer Initiative, and we continued enhancing the product and tested and retooled it based on feedback from regional and national stakeholders. It was tested in their operational environment and also eventually tested with the National Water Center, which agreed to take the transition to operations when it was ready. In the course of this, we found some unexpected uses, unanticipated uses, and those included fire managers and the famine early warning system. So we wrote another grant, and there was new CPO funding for the wildfire component. In about 2019, the daily product became operational at the water center, and that's the indicator of the Weather Service logo here. Also in the product developed a USGS data portal with them and a user guide. And where we stand today is that EDDI is disseminated and used via NIDIS dashboard, the National Water Center, the Western Regional Climate Center, and a number of other uses, and is used by stakeholders in agriculture, ranching, fire, and water that we know of. Third example is air quality forecasting, and this is for PM 2.5, which means particulate matter 2.5, and ozone. And the challenge was that the Community Multiscale Air Quality Modeling System, CMAP, used by NCEP and the EPA had huge errors. They hadn't been issuing PM 2.5 forecasts because they didn't think they had a good enough scale, only ozone. Their human health issues, increases in mortality are associated with PM 2.5 threshold that can be forecasted. So now it's being provided directly to state local air quality forecasters who use them, and there's an hourly product. And over on the right is an example of that product, and this is only being issued so far in Southern California, and it's based on the scale of the hour-by-hour PSL post-processing system. You can see a day's worth of forecast, and this is for a particular sub-area of the California South Coast Air Quality Management District. And you can see that they're forecasting unhealthy air in the early morning until about noon, and then in the afternoon it improves to moderate. So these kinds of forecasts are now possible. Another one of these idea to transition slides. In the early transition 2010s, as I said, there were these large errors in CMAC. At PSL, we realized that the post-processing skills that we had might help reduce the errors. So there's been several sources of funding, and initially in January 2016, the technique was proven and used in operations at NCEP for PM 2.5 that they had not previously had a forecast for. And then a couple of years later, in 2018, the technique was extended to ozone, so it was improved for ozone and used on operations. There was a Weather Program Office funding to develop and test enhanced processes for operations at NCEP, the Environmental Modeling Center, and that was successfully transitioned by the end of the grant in 2019. Just recently, EMC asked PSL to do some more enhancements, and we applied for disaster supplemental funds and got them. And this effort will enhance these predictions for the particulates that are related to wildfire and to make probabilistic forecasts. And that started earlier this summer in May. And then in 2020, where we stand is those forecasts I showed you on the last page. The first in US hour-by-hour air quality forecasts are being issued by our partner in California. All right, last of the major groups is knowledge transfer. Transforming science-based weather, water, and climate knowledge into actionable science for NOAA stewardship responsibilities. And so I'm going to give 3 examples of this. The first one is the Climate Change Web Portal, and it's first because it's kind of where we started with working with the Fisheries Service. Something that PSL has worked on for a long time is various ways of providing more efficiently ways to visualize and disseminate complex model output for researchers, but also for the core partners that we have. In particular, we had iterative conversations with NOAA Fisheries that informed the development of this. It had originally been started as a product for water managers, but the use by fisheries has really eclipsed that. They were very interested in being able to see certain kinds of graphics. So that led to pre-analyzed fields and graphics for targeted application. This had a number of feedbacks into PSL research, because then we did research that was aimed at some of the kinds of fields that they were most interested in seeing and some of the kinds of certainties or uncertainties that they were interested in. Originally, the funding was from Reclamation and the Army Corps of Engineers, and it's now funded by the NOAA Fisheries Integrated Ecosystem Assessment. That product has actually informed a number of conversations we've had with fisheries and has led to our work with them to do activities to reduce vulnerability and increase resiliency of fishery resources. And really what's been wanted in this is an ongoing engagement to provide the expert assessment, synthesis, and guidance to be used in policy and decision making, not simply a handoff of the product. And so with that climate portal, much of what happened was an ongoing conversation about what can you predict and how can you predict it and how well you can. That's led to PSL leadership and participation in Cross-Line Office Climate and Fisheries Initiative, which is designed to meet NIMP's climate information needs across timescales from a few weeks to longer term out to climate change. It's led to a lot of collaboration with fishery scientists to incorporate climate and ocean model output in ecological modeling. And from that, fisheries has evaluated management strategies to understand how sensitive they might be to climate change and other variability for a number of different species. PSL has participated in fisheries vulnerability assessments and scenario planning for marine species and habitats, including, as I mentioned before, integrated ecosystem assessment and the habitat blueprint. One example of this is the vulnerability assessment for the northeastern US continental shelf. It was the first of its kind by NIMPS, and our part in this, going back to the kinds of things that I talked about in the climate portal, is ongoing guidance and analysis of what the climate exposure is for a variety of different species, and depending on their biological sensitivity to change. The results inform adaptation of marine fisheries management and conservation to climate change and decadal variability. An indicator of their satisfaction with this work is that PSL has been asked to participate in future assessments, including those underway for the Bering Sea and for the California current ecosystems. And there's a peer-reviewed paper. The details are in the notes. A third way we've been working with fisheries is the interface of fishery and water management, but onshore. NOAA has authority over offshore ocean fisheries, but we also have authority over those fisheries like salmon when they come upriver to spawn. And so the challenge here has been balancing the needs for fish, the needs of fish, with flood control and reservoir water supply while minimizing the conflict among competing water users. We've participated in a pilot project called FIRO, Forecast Informed Reservoir Operations, that's worked to understand whether the use of weather operations can improve managing water in California Russian River Basin. That's north of San Francisco. And it applies PSL research on short-term weather forecasting to water management and marine resources. And it's been demonstrated that the improved forecast information can aid decisions by the U.S. Army Corps and other water resource managers. And an indicator of satisfaction with the work is that the U.S. Army Corps granted to their partners what's called a major deviation operations. This means that you can change the way their very formal operating rules are implemented. So for the next 5 years, beginning this year, they've been testing the use of the weather information in their reservoir operation environment. And if proved, it may be then lead to rewriting the water control manual for reservoir operations in this river system. And is now proposed for additional river basins. A second example of our work with fisheries is climate information to protect anadromous fish from hydropower impacts. The challenge is that fisheries wanted a better understanding of future risks to fish needs associated with the development of hydropower dams to protect the habitat based on downstream of those dams. NOAA Fisheries has a statutory authority to protect, mitigate, or enhance habitats for fish. And so when there's a reservoir proposed, they get to weigh in on this. We partnered with their efforts to understand the combined effects of hydropower facilities and climate change on anadromous fish, and to develop guidance on using climate futures and fish passage as well. Since 2015, we've done 5 of these projects, 2 on Susitna-Watana and 1 each on LaGrange Dam on the Tuolumne in California, Hiram Dam in Maine, and the Nyakook project, which is upstream of the very important Bristol Bay, Alaska fishery. Finishing up with assessment, I just want to note that assessment products that we've been involved in across the 3 PSL themes, water, extremes, and marine resources. Those are a few recent products, and the citations to all of those are in your notes. Wrapping up, I wanted to just now cross-reference the transitions that I've talked about with the three themes that we've been discussing. In extremes, several of the projects I've talked about relate to our theme on extremes. Several of them relate to water resources. Some of them relate to more than one, and for marine resources. So next to last slide is a summary of some of the PSL transitions that have been things that have been discussed in previous presentations, but organized according to the types that I've been discussing. So there's a number of modeling improvements that have been discussed in other presentations, some examples of enhancing NOAA products and services, in particular the various operational models that NOAA runs. There's several interesting analysis tools and data sets. The Arctic Diagnostics Toolkit is being used to assess the UFS performance compared to high quality observations. There are web-based analysis and intercomparison tools, and a whole project to do climate model visualization and analysis. I'll have URLs for those will be in the notes. PSL also does some instrument development, including unmanned, or the newer version is uncrewed autonomous aircraft system. We have one that's being routinely flown on the Hurricane Hunter. There's an ocean surface wave radar for looking at the surface of the ocean, and a snow level radar that's being used in California. There are some new products and services that have come out of PSL work, in particular the coupled Arctic forecast system. And I would call the S2S new forecast and identification of forecast opportunity, which were discussed in the extremes talk as some of those new products and services. And finally, just to reiterate knowledge exchange and use, which includes the ongoing work with fisheries, but for the water theme and for extremes, there's Army Corps work with the Army Corps of Reclamation and interpreting climate conditions. All right, almost the last slide. How do we do transition? We feel that we have an emergent strategy in these. First, some partnerships are deliberately aimed at transitions. Not all partnerships, but some of them need to be. We take some calculated risks. That means not everything is going to succeed, but we generally feel like we've learned something even when it doesn't. We recognize that there's a gestation period from an initial idea to spin-offs and transitions. I gave a couple of examples of these. Both of them happen to be about a decade from kind of an early idea to a final transition, although there were some interim spin-offs and transitions as well in both cases. Sometimes unexpected users and uses appear. We need time and resources to follow those two when we decide they're relevant. We've gained a lot from participating in test beds, both formal and informal, and feel that that has benefits for both sides. We've often found that the service activities that we participate in support our understanding of needs, our understanding of the broader science context, and is useful on both sides. We've actively participated in workshops with operational and other users, and this also seems to be a valuable use of our time. I mentioned the 2015 Climate Diagnostics Workshop, but we've also hosted the annual Fisheries Integrated Eco-Assessment Workshops in Boulder. By doing that, that's meant that some more PSL scientists have gone to those, and it's brought those people together to hear about our science as well. We've participated in the Weather Services Climate Prediction Assessment Workshops. I've been on the organizing committee for that a couple of times, and other use-oriented workshops with water managers and fisheries, and that's been valuable use of time. We've also recruited people interested in use-inspired work. PSL hosted the first 3 PACE postdocs, that's postdocs applying climate expertise. We subsequently hired 2 of them, and one of them is still with us. Kelly Mahoney gave the last talk on partnerships. We've also hired others that had existing user relationships, for example, with Nidus or with drought forecasting or with FuseNet. And that's just a couple of examples. So in summary, PSL uses a variety of strategies to understand NOAA operational and other users' needs and how we can contribute to them. Our use-inspired research strategies are designed to balance responsiveness to existing and articulated needs with innovation in anticipation of future needs or needs that haven't occurred to people yet. PSL cultivates a culture of transition-oriented science and partnerships. Our relationships with users has spurred use-inspired R&D aimed at improving operations overall, and those relationships have often smoothed the pathway to transitions or enabled them. And then finally, I want to note that PSL is sought out for novel research advances that have the potential of being transitioned. The panel and I will be happy to answer questions when we see you later in November. Thank you.